Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. In the public eye, it would appear that infrared imaging rode the wave of the pandemic to forge a robust connection with biomedicine. Handheld thermal devices were, for much of the pandemic, practically synonymous with COVID-19. Long a preferred modality in factory and industrial settings, imaging in the infrared came to prominence at the start of the current decade, and prominence is where today's guest on All Things Photonics has held it for the bulk of his career. Fresh off the heels of Photonics West 2023, Rohit Bhargava, founder professor in bioengineering in the University of Illinois' Beckman Institute for Advanced Science and Technology, joins us to talk new utility in spectroscopic infrared imaging. That notion, which served as the subject and impetus of his keynote presentation at PW's Optical Biopsy Conference, is top of mind for clinicians and engineers. As Bhargava explains, infrared imaging, be it for spectroscopy, microscopy, or any method, is subject to trade-offs between signal-to-noise ratios, spatial spectral coverage, resolution, and optical arrangements. The ability to manage and optimize these intertwined considerations has given rise to increasingly sophisticated instruments and improved outcomes as a result. In his conversation with Photonics Media news editor Jake Saltzman, Bhargava reveals how developments in instrumentation, the incorporation of AI and machine learning, and lessons learned from the conventional optical imaging roadmap are pushing infrared imaging to improved levels of speed, accuracy, and resolution. Bhargava, who also holds the role of director at the Cancer Center at the University of Illinois, then discusses streamlining the transfer of technology from out of the lab and into clinical environments. From within the University of Illinois ecosystem, Bhargava and his colleagues are applying core optical and photonic methods to some of the most demanding challenges characterizing today's biomedical climate. Insights on that topic, as we launch our venture into new utility in the infrared, are up next.
Your Photonics West presentation really focused on new utility in infrared imaging. In fact, that was the verbiage that you articulated there. When you're talking about new utility, that I think leaves the door open in a very pleasant way to talk about an emergence of modalities, use cases, techniques, and really just a convergence of all three of those things. What are we talking about when we talk about new utility in infrared imaging?
Exactly, Jake. So thanks. That I think you sort of captured the essence of what I was getting at. Utility was meant to be from multiple directions. Number one, obviously, on the instrumentation side, there's new capability that allows you new kinds of applications, right? So one is the traditional technological advance. The second is approaching new areas where infrared spectroscopy and imaging have traditionally not been applied, which is primarily in the biomedical space. And the third one, which is a more practical usage, was the intent was to convey that we're actually going to make it useful and usable by the non-expert spectroscopist. So somebody who's a domain expert can now actually use the technology rather easily rather than being a photonics scientist. So that's what we meant in all three areas. And again, it means new capability for research, also means potentially new capability for clinical diagnostics.
And so to have this discussion, certainly the need is there, the appetite is there. What are the drivers, not just for this presentation, but for the substance of the presentation, for making the technique, or the techniques, I suppose, more accessible and more practical?
So this is the classic, lifetime work of a person in photonics. You're trying to make measurements faster. At the same time, you're trying to increase the signal-to-noise ratio of your data. And third, of course, make the instrumentation cheaper, easier to use, and in other ways more accessible. And in infrared spectroscopy and imaging, it's a little bit complicated because your wavelength range is so large. And even though your signal is quantitative, the infrared domain has not been subject to the same intense development that visible wavelengths or near infrared for communications purposes have been developed. So it's still a little bit underdeveloped in terms of the technology of photonics. it is tremendously exciting, in terms of the applications, because we haven't explored the chemical world as much as we have explored the visible morphologic world, if you will. And actually that has become accessible now with increasing computation and AI and so on. And it's also tremendously exciting for things we haven't yet focused on discovering, which is really about pushing the limits, right? How can we push the limits of recording data faster? How can we increase the spatial localization of our signal? How can we, get much better data in shorter time? Those are all questions that are, age old, but again, it's a very, very critical time in the field at this point.
What has led to now being the critical time? Are we talking developments in the last 5-10 years, or have we arrived at a sort of the peak of the mountain in some ways?
No, I wouldn't say. I would say we're at the base camp of the mountain. I think there's a lot more to go. You can break down the recent, increase in activity to a few factors. One is that unlike optical microscopy, where you record the data and you can see your result right away, you actually need some form of computing to access the chemistry behind things, right? So computers needed to be capable, algorithms needed to be capable and usable by a wide community and so on. And of course, you can follow the revolution in computing. What we can do today was not even possible just a few years ago. The sophistication of machine learning methods today, our understanding of how to deploy them and use them is much greater than anything else. So one, I would say there's a unique synergy between IR imaging, chemical imaging, and computing. And because of advances in computing, we're seeing a benefit of those things. Second is the availability of new components. So quantum cascade lasers in particular, or tunable laser sources broadly, I think is a second big advance, and that's been well discussed many places. The third is more interesting. Many new people with new ideas who were not engaged in infrared imaging as a research topic have recently joined the community. So the number of people who are engaged in developing infrared imaging has increased, and that's great because it brings new ideas in, brings a diversity of thought. It frankly brings in more people to do more things that previously a few groups could not accomplish by themselves. So when you combine the increased ease of access of some instrumentation, the availability of computing and the ease of computing, together with new ideas and a larger group of people engaged in the research, it all makes for a very explosive mixture for this field, which we're seeing in front of us.
Well, it's so interesting from an outsider's perspective who has some knowledge of the peripheries of the field, such as myself, is that there's this, in addition to the synergies, at the same time, there is this contrast. And, we're not pitting techniques against each other, but you have infrared imaging, and on the other side, you have more conventional optical imaging. And I think that was, and correct me if I'm wrong, in some ways, the way you framed your presentation. I'm curious what the qualities or maybe the deliverables of this more conventional optical imaging, of those modalities. What do those bring that IR imaging typically has not been able to bring?
So that's really exciting. I think there are two things to imagine. One is what IR imaging has learned from other modalities, just without engaging any other part of the wavelength spectrum or any other detection technologies. And certainly the advances in optical imaging broadly also influence IR imaging, right? That's a straightforward benefit that we derive. But there's this very interesting rise of hybrid technologies. So you can do infrared excitation, optical detection, you can do acoustic detection or AFM detection, for example, right? So anytime you take infrared excitation, you can potentially obtain the benefits of infrared absorption, which is a really, really strong optical signal, perhaps the strongest optical molecular signal that we've got in terms of raw potential. But now you bring in a detection modality that takes full advantage from, say, the advances in optical imaging that have happened over the last century, or takes advantage of recent advances in acoustics, and even more recent advances in AFM technology. And with each one of them, now you get a unique set of benefits. So when you combine with optical microscopy, you can potentially achieve optical resolution, but with molecular chemical contrast that comes without the need to stain and comes from intrinsic composition. Likewise, you can do acoustic imaging in a non-invasive way, for example, and derive that. If you want ultra high resolution imaging with an AFM, of course, AFM technology is well known, but now you can derive molecular contrast from IR spectroscopy with an AFM. So just this amazing, hybridization of IR imaging with other technologies is leading to many, many new applications.
The benefits and functions of acoustic techniques in atomic force microscopy, or AFM, may be widely known, though their criticality to the hybrid modalities that Bhargava mentions remains somewhat unrevealed, at least within the biophotonics communities. While these imaging techniques continue to find plays in semiconductor materials research and chemical imaging, for biomedicine, the hybrid methods of which Bhargava speaks are a source of great excitement in the field, if even at times due to their novelty. For the IR community and the wider imaging community, motivations are sometimes diverse. Still, Bhargava says, fit-for-purpose instrumentation is a leading driver.
Can you put your finger on the story of how a researcher or an R&D group comes to decide or even to experiment with merging modalities to get to this hybrid approach? I mean, I have to think, just being at Photonics West, right, you take a wrong turn and suddenly you're in the AFM room or worse, the LiDAR room. I mean, you can go get lost in there. But there's such a potential, and it has to start from somewhere. So I'm just curious, from your perspective, how do some of this experimental activity begin?
Yeah, I think some of them, Jake, come from an instrumentation point of view. So they might be experts in, say, fluorescence or some optical microscopy technology, and they want to bring in this molecular recognition capability that IR promises, right? So they feel there's a gap in what they can measure, and using chemistry, they can fill that gap to get more information from their technology. The second is, of course, the IR community who want to address certain limitations imposed by wavelength, for example, or limitations of detection in vivo, for example, that might be difficult at this point with using all IR optics. And the third, I think, is also a really critical audience. It's those who have problems that cannot be solved by even a combination of technology. And they come up with new problems to the community, and specific solutions derived for a specific use case might be developed with IR imaging. But the overarching theme, whether you come from one of the three communities or a combination of them, I think the overarching theme is that there's purpose-driven development of technology, right? So fit-for-purpose IR microscopes, as opposed to just having, just even a few years ago, about a decade ago, really the only option was a Fourier transform infrared spectrometer with maybe a wide field detector. So you had one flavor of instrumentation. Now you're seeing many, many diverse kinds of instrumentation, each really useful for one particular purpose. Just like fluorescence experienced the same growth, right? So you had fluorescence microscopy, then you had 2-photon to give you better localization. You had in vivo to give you, ability to measure living systems, for example. And then you had intrinsic fluorescence versus, exogenous fluorescent labels. So you'll see the same evolution, I think, in this part of the electromagnetic spectrum in the coming years.
This, I suppose, picks up where we've gone so far in the conversation on the topic of instrumentation and pivots it. But I want to talk about one piece of equipment. I suppose we'll call it a piece of equipment rather than an instrument that has really driven quite a bit of positive change. It's been a real change maker, and that's the quantum cascade laser. What has the advent of the quantum cascade laser meant, not just in the infrared imaging community, but really the entirety of the imaging community?
Oh, thank you. That's great. It's one of the most impactful advances, certainly in our community. And of course, the benefits of lasers are well known, right? You can get the source to do things that traditional sources could not. But for us in particular, the advent of these tunable lasers that can be tuned over a wide broadband range has really been critical, because if you think about it, the total mid-infrared spectrum is about 20 times larger in wavelength than the visible spectrum, right? So that's a lot of real estate to cover. And making lasers that cover that traditionally in the visible region, for example, you could make a few frequencies, and those were sufficient for most purposes. If you were doing fluorescence, you excited a particular frequency, and 3 or 4 lasers would sort of help you cover most of the range. But in the infrared, that's not possible. You really need not only to cover a very large range, you also need the spectral resolution, because that's what gets you the right chemical information. So this challenge of getting a bright, stable source, perhaps, there are other characteristics that can be useful, but by and large, the largest idea was getting a narrow bandwidth frequency source that is tunable over a broad bandwidth was just the major advance. So number one, it allowed us to get away from, when it makes sense, away from measuring the whole spectrum. So traditionally, when you used an FTIR spectrometer, you would measure an extremely large bandwidth, not only for the ability to measure the full spectrum at one time, but also fundamentally to reduce noise and make sure that you could measure signals from even very weak sources, because that's all you had, weak sources. Now, instead of measuring a whole spectrum with, say, 1,000 data points, we're able to go in and measure maybe 2 or 3 or 5 data points that might be needed across that spectrum. We call this the discrete frequency approach. And really, this change came about 10 years ago, and when not only the advent of lasers, but with our group also, we developed filters that reflected a narrow band of frequency. And so many approaches to try this sort of discrete frequency as opposed to the continuous spectrum of FTIR came around. The brightness of the laser helps in this particular case because the multiplexing advantage that you get from FTIR is really, really strong. And certainly having a bright source goes a long way in obtaining high signal to noise ratio data. So at this point, what QCLs have really enabled us to do is go for specific frequencies, go for places where a bright source is really useful to excite maybe some processes that were not possible with FTIR with high SNR, or now really just go direct imaging and obtain very fast, high quality data.
You look at some of the results of your working group and others around the world, really, and you begin to sort of peel away and you can see how these lines of research came about and how different pieces of equipment and instrumentation have led to these types of advances. AI, and we'll get into AI because anytime you're talking about new utility, I think at this point in time, it's worth mentioning AI because it's here, and that's great. The promise of pairing AI with medicine specifically is really uncapped. It's also daunting, and I think you touched on this in your presentation too, because we're not just talking about the technology, we're talking about how do we optimize workflows in an actionable way, given the sophistication of the AI. Another perspective question for you. How do you look at AI, given that it is such a daunting yet really magical tool?
So AI for us, Jake, has always been an integral part of the chain, right? When you start doing chemical imaging, certainly with FTIRs, right, you had 2,000 data points per pixel. So how do you derive information from that? You certainly cannot do it manually, right? So from the very inception, we were using analytical tools, mathematical tools to derive information, right? At some point, that goes from simple analytical tools into the domain of machine learning and AI, more broadly speaking. So in my lab, we've been working on using machine learning to derive useful information from chemical images for well over 20 years now. And that has given us some good perspectives on how not only dealing with the evolution of AI tools, but also how to use them. And I can tell you it's just an amazing time to be in this field because the capabilities of AI today, the ability to use large amounts of data, the sophistication of understanding how that use works is just at a really, really high level that didn't exist just a few years ago. But what has not changed is the tight integration between understanding what the limits of your data are, understanding what your data is measuring, what it's not, and what parts and how to use your data in the right way as a feeder into whatever AI algorithm that is useful for that particular case. And again, the type of data sort of determines the best algorithm to use, and the availability of those kinds of resources often informs what data you acquire as well. So this interplay and actually the sequential staging of measurement, pre-processing your data and actually using a particular AI algorithm to derive information should be placed in the context of the problem that's driving all of this, right? So imagine the problem, instrumentation, and AI being pieces that you bring together into one really synergistic whole. And that's really the key to using AI.
Again, at Photonics West and BIOS, we talked and we saw about instrumentation and the power that smaller brings. It's a tough thing to put into words because it's not necessarily a new trend. The need to miniaturize and the want to do that is not new. So I'll ask you to do the impossible, put it into words. What really is happening in terms of miniaturization and how much progress have we made?
Significant progress. So the quantum cascade laser, for example, is one great trend. Our advances in designing new optics and getting them fabricated with the fabrication approaches available today is much larger. For example, we had reflective lenses for IR microscopy for a good 50 years. Those were the dominant technology, maybe even longer. And now we, like I presented at Photonics West, we have a range of infrared materials and infrared lenses available, and we actually built a new microscope based on refractive optics. Again, there are two big advantages there: the ability to microfabricate really precise optics that are needed on a one-at-a-time basis for IR imaging research. And the second is when you don't use a broadband source but use a laser, you can afford to refocus light, right? It might seem like a small point, but again, the bandwidth comes into play. Reflective optics afforded us a constant focusing capability, which now if we go to single wavelengths, we can of course move the sample and so on and refocus. So again, there's the ability to diversify your instruments has come first. And now when we are driven by particular uses, the push to miniaturize them, miniaturizing both the size and what I would prefer more is miniaturizing the cost of some of these components, right, is I think equally important. And I can bet you that we will see movements towards miniaturizing measurement devices, again, coupled to reduction in cost as these approaches become more and more common.
Doug Farmer, who edits our Biophotonics magazine, really has an excellent editorial board, including some of your colleagues at the University of Illinois. And one of Doug's takeaways that we spoke about in preparation for this conversation was not just miniaturization, but miniaturization paired with customization. Where's the line drawn there? Because it's very similar and there's a lot of overlap, but they're two very different desires, I suppose.
No, that's a great question. Maybe I'll take a step back and give you a little bit of a philosophical answer. So if you look at the field of IR spectroscopy, right, the fast Fourier transform really brought about a revolution in the 60s, which led to very early 70s Fourier transform spectrometers in the mid-infrared. And there was a huge burst of activity in the 70s and 80s that developed the interferometric technology, brought in microcomputers, interfaced, interferometers to other measurement technologies like gas chromatography and so on. And this was just a tremendous activity and investment in technology development, customization, hybridization of technology, and so on. And as that technology matured, there was obviously less to be gained by pushing it. And somehow that activity kind of declined over a period of years until imaging came along. And FTIR imaging really reinvigorated the IR spectroscopy field. And now there's, of course, the big explosion that we've talked about. So it really, the whole field has a history of customization and interfacing, hybridization, miniaturization, and so on. And I think, as I mentioned, we're at the base camp of the mountain right now in terms of customization. And there are a few groups now that are emerging that can make custom, measurement technologies. Certainly for a microscope, we've reported and other groups have reported custom microscopes, not just a single optical component backfitted to a traditional microscope, but a whole microscope design, a whole new design that takes advantage of new optical components and also new detectors and new sources.
Your wisdom does not just manifest itself in your ability to talk about these trends and technology areas with me. It also shows up, of course, in real results. And as director of the Cancer Center at the University of Illinois, it is of the utmost importance, your work. This notion of cancer research envelops quite a broad range of different types of science. And we're talking about diagnostics and pathologies, the epidemiology, a lot of branches out from that platform. With those in mind, where are we today in cancer research? And I realize that this is another sort of table setting type of question, but I think it's important for our listeners when the topic is so broad as this.
And thanks, Jake. I think, again, the motivation for our Cancer Center actually can be traced back to how we think about advances in optics and photonics and broadly. So when we started thinking about this about a decade ago, so in 2010, I had almost established my career here at Illinois. I'd started here in 2005, and we built the new bioengineering department starting then, and started thinking about what's really an important problem where engineering and technology can have an impact. And it was clear in 2010 or so that advances in cancer required us to take the recent advances then in molecular biology and turn them into useful technologies. So when I looked around the country, there wasn't a place that was focused on making those advances. Like there were people who were doing great science and they went out and found a clinician, for example, and were able to translate those. But the fundamental engineering and only focusing on that was a gap in the country that we saw at that time. So I was really grateful the University of Illinois took on that direction, and we all worked together to form the Cancer Center. On the path to that, we also discovered that, well, that same argument can be made for all of medicine. So we now have an engineering-based College of Medicine. So not just the Cancer Center, but also all of medicine is sort of trending in that direction. Of course, the College of Medicine is focused on educating the next generation of physician innovators to take these kinds of technologies on. And the Cancer Center has continued to advance on the research front, trying to promote fundamental engineering technological developments that can be translated into cancer. And that's our mission. And we think that's a unique space in the country that we can help fulfill. Also, from the use case side, if you think about cancer as a person trying to take care of patients, or even as a patient, there are two trends that become really interesting. So cancer is such an acute disease that anytime there's a diagnosis, you want to intervene quickly and with a sense of urgency, and rightly so, right? Any of us who've had family members or others who've gone through this process want this taken care of right now. So there's a lot of activity in the cancer world, even on the research side, that is very geared towards short-term developments that can be applied as quickly as we can and deriving even the smallest advantage that we can, but right away, right? So this sense of urgency is necessary in cancer, but not necessarily the way we need to think about it long-term. Right? In the long term, we all know that investing in R&D, investing in basic science, and building up from that foundation to have impactful technologies and bringing the revolutions of technology in the last 2 or 3 decades to bear on cancer will require us to go back to the drawing board. Something that is, a research tool, for example, cannot just be taken into the clinic. We really have to do technology from the ground up to make sure that it meets the right trade-offs in terms of offering the best possible performance, but at a reasonable cost point, right? So this re-engineering of technology or discovery of new technology and moving it to use is really the cause that we have taken up in our Cancer Center. We think of our Cancer Center as the engine that powers discovery to use, right? Discovery to application, discovery to translation, and so on. And we're promised to restrict ourselves in some way and focus ourselves on really the technology development piece. And then we'll collaborate with medical centers across the country to help translate that. We'll collaborate with them to learn about problems and get inspired on what to solve. But then we'll go back to the drawing board as an engineering powerhouse at the University of Illinois and take all that expertise that we used. For example, the inventor of the MRI was a faculty member here. The inventor of the LED, the visible LED, was a faculty member here. The graphical web browser through which we're talking, the first really major graphical web browser came from the University of Illinois. So how do we take that culture, that infrastructure of discovery in major engineering tools and bring it to the service of diagnosing cancer better and treating cancer better? That's really the point of our Cancer Center. And, we don't want to really restrict it to our campus only. We hope that we can make this a center where anyone in the community can come take advantage of those resources and work with us to really make it a better place for all those engaged in taking care of people with cancer and all those people with cancer.
The ways in which you've structured the concepts of engineering and technology just on a surface level seem to me that they might simplify this transfer of technology, which is unavoidable. There has to be that transfer, even if you're working within the same center. Is that a fair characterization for what you've been able to do at the University of Illinois? Have you sort of streamlined this process that is really important in getting something from a laboratory setting into a more clinical environment?
Indeed, Jake, that's really our goal. But, it doesn't happen overnight, right? It requires infrastructure. It requires support, financial and and also leadership support from any organization. It requires a culture that takes time to set up. It requires us to train, young scientists in a way to think like this, that it takes time for us to spread the word and more people to join the effort, for example. So I think we've started again. I would say we're a little bit further along than Basecamp, but certainly it had to start at some point, which we have, and it's gathering momentum as many of our recent efforts kind of show. But exactly this point of systematically taking technologies and bringing it to bear on problems that are identified, and also doing it in a very rapid fashion, as rapidly and as quickly as we can by removing all the barriers in the middle. So bringing a sense of urgency, not just a sense of discovery and a sense of development to the process.
In June of 2022, the photonics community was saddened to learn of the death of Gabriel Popescu, a quantitative imaging luminary and the William L. Everett Distinguished Professor in Electrical and Computer Engineering at the University of Illinois. Popescu and Bhargava, with Professors Stephen Bopart, Mark Anastasio, and others, formed an acclaimed and influential team for the biophotonics and optical imaging communities. Now, thanks to the newly opened Center for Label-Free Imaging and Multiscale Biophotonics, known as CLIME, a joint effort between Bopart, Mark Anastasio, and Rohit Bhargava, the vision and influence of Popescu's effort is poised to continue at the University of Illinois. The center's primary goal is to create optical and computational imaging technologies that can serve as a resource for clinicians as well as other investigators in the biological and medical sciences.
One of the things at the University of Illinois that touches the Cancer Center and Beckman that we can see is the arrival of CLIME, and that's the Center for Label-Free Imaging and Multiscale Biophotonics. And that's a development that I have to think brings a number of different emotions, given that we lost Dr. Gabriel Popescu last spring. And you knew the scientist behind the science. Can you put into words what his influence and what the influence of CLIME is going to bring to the biophotonics community?
Yeah, I think this is very bittersweet, Jake. I think the really amazing thing is that CLIME is a culmination of Gabby's vision and his collaborative spirit in many ways, along the lines of what we were just talking about, in trying to bring fundamental advances in technology into more hands and solving more problems, right? That was the underlying spirit of the CLIME Center. And of course, as you pointed out, Gabby Popescu led the effort on this campus with several people, not just on this campus, but also many collaborating groups across the world with this center. So we were, of course, devastated with Gabby's passing, and the CLIME was really, the CLIME Center was really his vision and his effort, in leading it. We're very fortunate that Professor Stephen Bopart, my colleague here in Beckman, agreed to step in for Gabby Popescu, and Mark Anastasio, who's an expert in AI and also has tremendous experience as the department head here, was able to step in and also take on expanded roles in the center. On the technology side, and again, we needed somebody to still contribute, I was asked by the team to help with some of the things that Gabby had planned to do. So again, being a person in the optics world, and we have a very nice group of people here with Mark and Steve both. I think with the three of us, we'll try to continue Gabby's vision, try to bring in technologies that are developed all across the Beckman Institute and CLIME Center into more hands, and hopefully try to accomplish the work that Gabby had really envisioned in the beginning, but also maybe expand on his work and honor his legacy that way by really expanding the impact, to more technologies, more diverse areas as the center starts to mature. One of the really interesting things that had been built into the center from the ground up was sharing of information and training the next generation. So there's a lovely workshop component. There's a very high collaborative component as required by these kind of centers. And we hope that it establishes a community that is much stronger in the spirit of how Gabby tried to bring people together for many, many years to come.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.